So for those on the phone, welcome to the SAE CDS Webinar Series. This is the first one of this series powered by Cummins. I am the HSE leader for the electrified power business. I'm Stuart Davey. I'll be talking you through this evening's slides. My aim is not to teach you how to work safely. My aim is to make you think about safety. If I can do that, then that's half my battle won. So when we start up a new project or a new business or a new application, one of the first things we do in the safety world is we look at identifying hazards. You can see there is a number of hazard types on the vertical axis, and then there is a operational across the horizontal axis. So a lot of this stuff here, although it relates directly to automotive and road vehicles, applies equally whether you're doing mechanical combustion engine or electrical powered. So it's a good start point. The ones identified in yellow are directly associated with batteries. So what I'm taking you through tonight is a subset of some training that I give to all of our incoming staff that work in the electrification business. We're going to talk about why the training is important. Actually, we don't talk about terminology. You're all engineers. I took that out. Some of the potential safety hazards, of which we identified nominally about 8 generic hazards that we need to be aware of when we're dealing with batteries and high voltage DC. The presentation only talks about direct current. I don't talk about AC. They are two different fish and should be treated differently. I also only talk about voltages less than 1500 volts DC from a legal protection point of view and from a safety under OSHA. But once you get above 1500 volts DC, you're into a whole different world of HSE controls. And what I'm not going to do is provide enough information for you to safely remove the covers of high voltage battery packs. That needs to be covered by your own documentation and your own procedures. So what you're looking at here, this is a 2001 BMW F1 car. This was when the energy recovery systems first came into use.
L'immagine esclusiva di Railsport vedete qui nel tratto del meccanico che riceve una scossa pesantissima appena sfiora la carrozzeria in fibra di carbonio, potente conduttore elettrico. Una scossa elettrostatica esplicitata da BMW, ma se pensate che nel CARES si parla di tensione tra i 250 e i 650 volt, si può ben capire il rischio corso dalle...
Apologies if it being in Italian, but it was the only footage that I could find of that. That was an F1 car with an early energy recovery system. It was an AC-based system, which is why he flew through the air and didn't get himself attached to the vehicle. One thing that's changed, and I believe it's the same with electric Formula SAE Electric, is that you also have a floating ground now. In the early days of KERS, we used to use the chassis as the ground, and this is why he managed to complete a circuit through a hand to an elbow contact. This is a little bit of background about why, from a business and for all of us exploring batteries, it's a new area of technology. And already it's getting a bad press in some circuits. So this is a little bit of background about Tesla.
Went up in flames yesterday. I could feel the heat in you. Oh, that's a Tesla. It was the perfect storm Wednesday when this video, along with an investment analyst downgrade, sent Tesla's stock price plummeted. Shares of Tesla Motors Incorporated fell 12 points to $180.95, a whopping 6% drop or a $600 million hit to its market cap. Although the Tesla S in the video was burned beyond repair, there is good news for the car company. Fire never made it to the passenger cabin, and the Tesla warned the passenger to pull over in plenty of time. According to the fire department, the driver struck some kind of object on the freeway. So why would a car fire that left no one dead or injured affect stock prices? Well, there's a few reasons. For one, according to the Los Angeles Times, safety officials have been tracking fires on electric cars out of concern that the lithium-ion battery systems might be fireproof. Earlier this year, Boeing 787 Dreamliners, which also use lithium-ion batteries, were grounded for 4 months after one plane caught fire and another overheated. Also, Tesla has a reputation to uphold.
And the headline really says it all. Tesla Model S achieves best safety rating of any car ever tested.
The Model S scored so well, the NHTSA doesn't have a star rating high enough to award the correct number of 5.4 stars. After being dubbed the safest car in America, you try to avoid viral videos of your car on fire. But Tesla released a statement on the fire and says the car's design is actually what kept the driver safe. A fire caused by the substantial damage sustained during the collision was contained to the front of the vehicle, thanks to the design and construction of the vehicle and battery pack. This is the biggest one-day drop in share price for Tesla since July. But to be clear, the company is by no means reeling. Shares of the company are up 400% this year. And as a writer points out, the Model S may still be the safest car on the road. Lithium-ion batteries pose a new kind of risk, but for now, there's nothing in this case to suggest they're anywhere near as plentiful as the gallons of gasoline millions of drivers rely on daily. For Newsy, I'm Jamal Akers.
So why is that important? The reality of it is we're exploring new technologies. When things go wrong, it makes big news. There are 31 vehicle fires, highway fires from gasoline-powered vehicles every hour in the northern US. They don't make the local news generally. You get one Tesla catches fire, and it makes international news. So we all have to maintain the integrity of this business and this science and the technology moving forward. So I want to talk about a few other areas where things have gone wrong with lithium-ion. 2012, in the GM laboratory in Detroit, they were doing some destructive testing of lithium-ion batteries. Destructive testing is part of the development process if you're developing new chemistries and new battery pouches and the like. They had an explosion in a test cell, probably a climatic test cell, reading between the lines of this one. Put one person in hospital, and just to put it into perspective, it did some $6 million worth of damage to the building. So when lithium-ion batteries go bad, they can go bad very quickly and in a very big way. Just be aware of what you're doing and think first. The next one I talk about is the Samsung Galaxy Note 7. And for those in the room, anyone got any idea how many batteries worldwide were affected? Anyone take a guess? 365. You'd have thought from the news that they were blowing up every other minute. The reason the Galaxy Note 7 failed was due to a cost reduction exercise. The insulator inside the pouch was cost reduced down and reduced from about 35 microns down to 15 microns. That probably saved Samsung on their cost to build each battery 0.002 of a cent per battery. That cost saving cost them an estimated $17 billion to recall every phone. Once you get out in industry, you'll understand that recalls are a really bad thing, both for reputation and finances. Talking about fire, the cells that we use, generally speaking, in most of our high voltage DC packs are those that we use in Nissan Leaf, manufactured by Nissan. There's only been one reported incident of a Nissan Leaf fire that may have been attributable to the battery pack, out of some 300,000 Leafs sold globally as of 2018. Again, no one was hurt in the incident. The BMS did its job. It warned the occupants. The occupants evacuated the vehicle. And as I just said earlier, some context, there's 31 vehicle fires per hour, not per day, per hour in the US, with one death per day. So some really rough, and these are sketchy statistics. That's some 95 per billion miles driven. By comparison, for the Leaf, that's less than 1 fire per billion miles driven. And if you take the statistics even sketchier, you can go up to 100 times safer than a conventional vehicle in terms of fire. We look here at 40 litres of gasoline. This is suspended in air. This is an ideal atomization test and fire, but this is 40 litres of fuel.
Our 40 litres of petrol are primed and ready. 3, 2, 1.
Lithium-ion, by comparison, in the early stages of failure, is a much slower reaction. So we look now at the HS SAE in this case is not health, safety and environmental. This is the Health and Safety Executive in the UK, which is the equivalent of OSHA. Actually did some work to look at the risks directly involved with battery vehicles and range extender vehicles that were different to a gasoline-powered vehicle. The key ones for most of the work that we're doing here is the presence of high voltage components and cabling capable of delivering a fatal electric shock, storage of electrical energy with the potential to cause explosion or fire, manual handling risks associated with battery replacement. As those of you involved in the electric car know, those cells are heavy. I imagine that's not an easy job to replace them, having looked at the car now. Potential for release of explosive gases and harmful liquids if batteries are damaged or incorrectly modified. The takeaway here is damaged and incorrectly modified. If you see batteries that are damaged, whether it's from an impact or other cause, then you need to do some careful analysis before you decide whether that vehicle is touch safe and how you're going to approach to the recovery of that vehicle. And then the potential for electrical systems to affect medical devices such as pacemakers. That's not necessarily an obvious one. We'll talk about that a little bit later. So if we talk about a typical lithium-ion pack, this is one of the Cummins ones with 15 individual modules inside the pack. This is a 74 kilowatt-hour pack. To give you some sense of scale, it's about 5.5 foot, 6 foot long, by 4 foot wide, by about a foot deep. There are, as most of you know that build them, mostly lithium-ion cells. And here we start to look at the different safety levels, levels of protection. There is internal fusing. Presume you're using fusing as well in your pack. I'm looking at the electrical team here for a nod. Yeah. We also use in automotive world, we use what we call a manual service disconnect. This is generally placed halfway in the halfway point of the pack, so you can, by pulling this out, you can split the pack voltage by half. So if you do have a short or other incident, it reduces the exposure. A number of contactors. Automotive, we use 2, mostly for fault tolerance, one on the positive and one on the negative. And then the BMS itself is the main structure for protection. The direct hazards we're going to talk about tonight are electric shock, high currents, magnetic field, arcs, water ingress, cell venting, fire, and weight. There is some interrelation here. Large magnetic fields are created by high currents, and there are some safety limits, for example, on energy, but the actual hazard is related to something else on that list. The electric shock is the one I spend the most time on. It's the one that's going to kill you. The rest of them are generally survivable. This is my favorite TV program when I was about your age.
Can you do your job whilst being electrocuted? Teaching, a hard job in anyone's book. Is it any harder if you're plugged into the mains? Strap some low-amp 9-volt electrical equipment on this Harris, and with the help of Class 6A, there's only one way to find out.
Let's take our register.
Taking the register is traditionally the first job of the school day.
Emily.
Important to keep it tidy. Not happy.
Robin.
Okay, that's Robin back twice.
Jen.
Not a good display, but jerking in pain she must be, she just finished the job.
Thank you.
On then to maths.
Hands up if you can tell me.
Putting your hand up particularly hard when a muscle spasm brings the arm to down.
This teacher's self-control while executing an electric shock is unbelievable. My language would be not repeatable. One thing to correct here is it says electrocution. Electrocution is a one-time event. It is not survivable. So what's the problem with electric shock? Your body is a natural conductor of electricity. When we look at the video of the DC charge being put through, it causes muscles to contract. All of our muscles work by electrical signals. And generally, when we look at electrical signals and muscles, the contraction side of your body is always stronger than the extension side of your body. This is why when you see people get hold of a DC shock, it pulls me in. It's difficult to let go. We worry, generally speaking, about a hand-to-hand flow across of current. It is possible to get hand-head, head-foot, although you have to be trying quite hard in most circumstances. The issue that hand-hand is particularly dangerous is because it takes the electric charge across your electric current across your chest. If that current is too big, then the muscles that are controlling your heart and lungs can fail. They can go into an imbalance, or they can stop completely. What we'll look at now are different voltages here. So this table is taken from some IEC data. When we talk about the safety world, we look at a number of sources of where we can find information. There's not a lot of work done on the high voltage packs. We look at the zones here. The light blue zone is what we refer to as the DC1. This is like putting your tongue on a 9-volt battery. Some people can't even feel that. Many of us can. They feel it as a slight tingling. DC2, which is the green zone here. This is like if ever you had a TENS machine used or electrical stimulation at a chiropractor, where if you wind it up, it is quite possible to get a full limb jumping up and down uncontrollably, but it won't do you any harm. DC3 is where we start to get into that danger area. And just for point of reference here, if we look at the time here, we're at 200 milliamps and less than 10 to 20 milliseconds of exposure. So it doesn't take long. Generally speaking, if you get shocked at DC3, it's a reversible process. When we get into DC4, the red zone, I refer to it as the death zone. If you survive that, consider yourself lucky. If we look at a Cummins battery at 650 volts DC, depending on its state of charge, it has a short circuit capability of 8,000 amps. If we look at the graph on the screen, we're at 10 amps on the far side of this screen. If we take that out to 8,000 amps, we're in another building. You really do need to be careful with high voltage battery systems, particularly next year when you go up to doubling in size. As electric shock happen, you have to have contact with two different voltages. There has to be a potential difference between them. So typically in our case, it'll be the positive and negative terminals of that battery, or a connection, or a lead. For current to flow, there has to be resistance. Work has been done on measuring resistance. If I was to get an ohmmeter here and pass it around the room, we get some 60 different readings. Every one of us is different. We're different on different days. I hate presenting, so my hands are really sweaty at the moment. That reduces my resistance. Cuts, damage to the hands, all reduce your resistance. When we talk about low voltages at less than 100 volts, there is a difference between the percentiles of the population. Looking at the graphs, this is 50th and 95th percentiles. So 95th percentile of the population is someone my size, 5th percentile is an average female, and a 50th percentile is somewhere in the middle. But everyone is different. When we get out to typical pack voltages, yours is the Purdue one, I think, is around 300 volts from memory. You start to narrow that gap down. We're all treated the same. We take that now and look at that current plotted against voltage and current. We see that we talk about the SAE between 300 and 600. You're at 600 milliamps, typically, for a 5th percentile. 600 milliamps on this graph takes you already into the death zone. It really is that dangerous. I should point out that there has been no known electrical accidents that show an electrocution below the C1 curve. The C1 curve is in the yellow. But with all standards and all recommendations, there's an element of safety involved here. So the skin is a significant part of your total resistance. If the skin is damaged, the resistance can be much lower and the safe voltage decreases. This is why we don't ever give a safe voltage for people and individuals to work out to be exposed to. There has been a reputed case of one person being killed using a 9-volt DC. When the skin was broken at both the entry and exit point, this had to be a man. I know no woman that I've ever met that would have ever even thought it was a good idea to try. Allegedly what he did was he took 2 hypodermic needles, put them into his hand, and then connected a 9-volt supply to it. There's some questions on that. My reference for that is the Darwin Awards, but generally speaking, there's no smoke without fire. Someone's tried it and someone got hurt at some stage. Don't try that in the lab. So when we talk about electric shock, what do we generally consider is a safe electrical voltage? Both OSHA and NFPA and Cummins look at 50 volts as the break point. At 50 volts, the chance of you being hurt by an electric shock are near zero, but again, everybody is different. A lot of automotive standards, the SAE, for example, and ECE Reg 100, which is the European standard for electric vehicles, looks at talking voltages greater than 60 volts and less than 1500 volts DC, or greater than 30 volts and less than 1000 volts AC. There are exceptions to this. Some industries that use a higher limit, forklift manufacturers and forklift batteries are around 80 volts, but their manufacturers don't consider that an electric shock. Risk. So if you see somebody exposed to an electric shock, what do you do? The first thing to do is to determine whether the patient is safe or the victim is safe. But there are some electric shocks that we don't ever bother to report. First one here is static discharges within reason. I don't know what you've got in electrical labs here. I'm sure that there are. It's possible to generate some very large static charges, but general static charges that you see exposed to daily, you wouldn't have to report. Minor singles, those with induced voltages, electric fences, induced voltages around substations, and then voltages less than 50 volts. What I would say is everybody is different. And if you have a friend or a colleague or a teammate that you see is exposed to electric shock, keep an eye on them. The effects may not manifest themselves till afterwards. So even if it's someone that's less than 50 volts, just keep an eye. Be ready to report it. Do you have safety procedures on what to do in the electric shock? Yeah, so you have a policy or procedure to follow. The next stuff I talk about now is how to avoid an electric shock. It's really simple. You stay away from the electricity. If you're not working on it, and you don't need to have your hands inside where the batteries are and where the connections are, stay out of it. One thing of note here is the NFPA 70E defines that there should be a minimum boundary distance for a given voltage. We generally work at the 300 to 1 kilovolt range, which dictates that there should be an approach boundary of at least 1 meter or 3'6". So consider getting straps and consider getting tensor barriers and stuff so you can keep people away when you're doing exposed electrical work. How do we at Cummins control access to live electrical equipment? First thing we do is we generally control access to the workshop area. You may want to consider locking batteries away or doing batteries away out of the way of the general access to your labs. We use some signage which shows the current state of the equipment. We use 3, so we use a danger the HV system is live. A notice if the HV system is disabled, and then we also use a danger sign, which is on there, which says that there are exposed live electrical connections, conductors rather. Where possible, use a lockout tagout procedure. I'm not sure whether you use lockout tagout. It is the only safe way to do it. I know you have to have an electrical safety officer as part of your team. Consider putting some locks, consider removing cables and some lockout equipment. That person has access to the only person that has that key. We always try and have an AED in near proximity, certainly within 50 yards of where we're doing exposed work. If we talk about HV rescue sticks, these are on the bottom right-hand corner. These are designed to pull the victim away from the electric source. And for our batteries, and you'd have to do the calculations on your ARC incident rate, we look at using Class 0 Type 1 insulated gloves. So again, to reiterate, how do you avoid it? Stay away from it. Keep people away from it. If you've got somebody doing exposed electrical work, don't distract them. Let them focus on what they're doing. If you're having to move the packs, follow the instructions and the documentation that you have to guide you. If you need to use it and run tests on it, again, follow the instructions. And this is a fairly big one. If the pack shows any signs of damage, evidence of liquid ingress or egress, or smoke coming from the pack, then report it to your course supervisor or the HSE supervisor within the lab. This equally applies if you're in the paddock at an event. That needs to be reported and dealt with quickly. I'm not going to talk through this slide. I'm sure somehow this is going to be handed to you by some mechanism. This is our starting point for how we look at developing a lockout tagout procedure for a vehicle. And it's just that shutdown system. Consider disconnecting HV cables from the batteries and locking them away. Mentioned MSDs earlier. These are examples of the MSDs, and although they're on the outside of the pack, they're generally at the midpoint of the modules inside. Some have removable, some are actually lockable, very similar to the master switches that you already use on the car. But all of these have a high voltage interlock loop that is integral with them. So if anybody tries to pull that plug out, it breaks the low voltage circuit, which means your contactors drop out and you remove the high voltage source. Yeah, it's a mechanical disconnect. You're effectively removing about 4 inches of HV cable from inside the battery. And generally it's a 2-stage removal operation. So the first stage breaks the HVIL, the second stage of removal then breaks the high voltage, or removes a section from the high voltage. The HV current itself should have gone away as soon as you break the HVIL. These are fairly readily available. And almost all road-going battery and range extender vehicles use these. We also use these lockout covers where you remove the HV cable, so if you have a plug-in cable, and then you can lock it around to stop somebody plugging cables back in. Consider if you are going to use an MSD, these lockout boxes, where you can see here again that your electrical coordinator, electrical safety officer, is the only person that has the key to that lock. If you have specific instructions for your pack design, I do recommend that you write specific instructions, whoever's in charge of the battery, follow them. Make sure there is no area around where make sure the area where you're working is designated an HV activity zone. It's really easy to make some simple signage up to keep people away. Most people will stay away from a warning HV present. There are exclusions, usually electrical engineers. But most people, certainly mechanical engineers, will stay away if you show them electricity. Always use tools that are insulated and rated to the voltage of the pack. So for example, up to 1,000 volts, any multimeter you use has to be a Cat 3000 volt multimeter. Tools, again, should be certified by an accreditation lab. Eye protection, insulated gloves, assuming the pack is less than 750 volts, class 0 gloves will keep you safe. Bear in mind that gloves need to be tested every time you put them on. They should be inflated and checked for leaks. If a glove leaks air out, it is not going to protect you. You should always use insulated gloves with a leather gauntlet over the top. But we do, by permit in Cummins, say that if that limits your dexterity too much for making fasteners and stuff, if you're inside a battery, we allow single-handed working. If you're working single-handed, there's not enough potential difference generally across the areas you're working to deliver a dangerous electric shock. But I would make sure that you don't do that as alone. We always have 2 people working on a pack at one time. One person is there to do the work, the second person is there to monitor. That means not checking cell phones, that's not Snapchat, that's not Facebook, that is I am watching out for my friend and teammate while he is doing the dangerous work. And we say with the manual service disconnect, it's the first thing you ever disconnect when you work on an electric vehicle, and it's the last thing you put back in again. This slide is for the HSE geeks amongst you. This is the actual standards that are required. When we look at somebody that's received an electric shock, the first thing here is do not rush in. look, evaluate the situation. Do not directly touch the person with your bare hands. Even the packs that you have more than enough voltage and more enough current capability delivery to kill more than one of you. If possible, hit the e-stop, break that source. If that's not possible, look at using gloves or a rescue stick to remove that person from the energy source. What I would say is it's a rescue stick. It is not a tickling stick. It is not a hugging stick. You will have to use force to remove that person from high voltages. And even if you put a slight hole in their skin, a few stitches is not a big price to pay for survival. If your victim is responsive and alert, get them to a medical department or first aider. I don't know what the policies and procedures are here in the university, but it might just be call 911 and probably alert the local police or emergency response team. If they're not available or while you're waiting for them, check vital signs. If you can do CPR if there's no pulse present. And be aware, even if that person is slightly responsive and pale or faint, there is still a risk of them going into shock. Keep the victim's head down. Lie the victim down with the head slightly lower than the chest, with the feet elevated. A big electric shock requires hospitalization. It is not enough to get the shock and go, man, that stung me a bit. I'm going home now. Never underestimate the severity of an electric shock injury. This is a slide that you can use. We use this as a general notice. We put it in vehicle logbooks and the like. It's just a continual reference. It just brings things fresh into people's minds and gives you a step-by-step how to do it. One thing to note, if you can't get an ambulance, make sure there is a driver and another person as well as the victim. That other person carries an AED to get the victim to the hospital. The beauty, if you have got AEDs on site and access to them, once those pads are on the chest, that's monitoring. It will tell you when you need to stop the vehicle and give that person a shock if necessary. When we look at HV battery packs from manufacturing, as I said, we use a floating high voltage connection. I believe you do the same as part of your design and connections of HV on the vehicle. So there is no correct connection to ground or earth in a correctly functioning pack. Be aware if that pack's damaged, there may be a route to ground. There is typically, certainly in automotive packs, a high resistance connection which we use for measuring ground faults as part of the startup before we engage the contactors. This is a high impedance connection, typically over 1 megaohm. And if you do the simple maths, even at 1,000 volts, that's a current of less than 1 milliamp, which most people don't even feel. This is why we talk about the hand-to-hand current path. It's the most obvious route for you to get an electric shock, and it's the one that's likely to cause you the most damage. If ever you use ESD, electrostatic discharge protection, remember that's there is not to protect you, it's to protect the electronics on your car. And again, that's a high impedance connection. Goes safe when it's dark. The reason I show this slide is the routes to ground are not always obvious, particularly if there's damage to the vehicle. If you hear rubbing when the car comes back in, check that your battery pack's not dragging on the floor. It sounds obvious, but just think before you approach vehicles. So in summary, the HV generally is not connected to ground, so to get a shock you need to find some way to touch the HV positive and the HV negative. In automotive world, we use a touch-proof connector, which has about 1/4 of an inch diameter. Now, unless somebody's got really small fingers, it's impossible to touch those conductors. High voltage connections are not present if you have an MSD and it's removed. Even if you have the MSD present and your systems are the same from what I've read of the rules, low voltage must be present and the correct instructions sent to the pack via CAN to power it up. And there also has to be a demand from the system as well, again, before the battery will generally deliver voltage current. If there is a ground leakage present, and I think you use ground leakage protection, you don't use an isometer? I don't know anyone? No. Again, certainly in an automotive pack, which is exposed to the greater population, we use isometers at various points throughout the system to look for ground fault detection. If you have a touch-proof connection, high voltage connection, even with the pack powered up, it is possible to disconnect it. The automotive connectors have the HVIL loop in them, and again, if we disturb that, it's a two-stage pull-out. It is a way to remove power. You really shouldn't do that, except in emergency situations, basically because what it does is it creates an arc across the face of the contactors, and your contactors then become unreliable. I mentioned the HVIL. This is very much in use in automotive. It's the high voltage interlock loop. If ever you look on NFPA 70E First Responders website, where OEMs are asked to provide information to first responders on how to make EVs safe, what they are doing is giving a cut point into that HVIL. Being a mechanical engineer, I describe this as a single cable that runs through every component. My control and electrical friends tell me that's not at all how it's designed, but it works for a description. This is a very typical layout you can see here. You see there's multiple sections of it. And again, the purpose of this is to drop the low voltage wire connection, and that drops the contactors before you can get a chance to receive that HV shock. So think about what you're doing. Keep the place tidy around. You're in a very small environment here at Purdue in your lab. When you're doing battery work, make sure it's clean and tidy. Make sure there's space around you to respond should anything happen. Use the protective devices available. Safety glasses is an obvious one. Think about things if you're wearing neck chains, rings, watches, belts even. Take them off, insulate them, wrap electrical tape around rings, remove neck chains. There is always the option of keeping one hand in your pocket, and really just don't take shortcuts. Think about every step you're doing. And if anything, all else fails, ask for assistance. That's all I talk about on electric shock. Has anybody got any questions before we move on to the next section? For those of you on the WebEx, if you've got questions, if you just put them as a message, and we'll look at them at the end, because I can't see them while I'm presenting. So high currents are the next risk we talk about, or next hazard we talk about. What you're looking at here is 500 amps pulling through 1 volt in a 100 amp bus bar. The real danger from most exposure to high currents is the high temperature in external wiring. If your wiring is poorly designed, if you've used the wrong spec cable, they will get hot. That then can lead to other hazards such as fire. The high magnetic field is a resultant of pulling a high current. Again, when we design, and those of you that are working on BMS design, make sure that you have safety interlocks before you can deliver that high current. If those limits are failed, the next step generally is that the fuse fitted inside the pack will fail. The EU very kindly provides some directives for looking at electromagnetic fields, which is our next hazard. There are 2 hazards associated with electromagnetic fields. The first one is the movement of creating a ferrous projectile risk. So if you have coiled cables, you can move ferrous objects. And then the next one, which is the really not obvious one, is the static magnetic fields. This is how implanted medical devices are programmed. So if ever any of you have implanted medical devices, like pacemakers and AEDs, make sure the rest of your team knows about it. The battery itself and the systems are switched off are not going to harm you, but you may notice that field should you become in close proximity. It doesn't stop the device, doesn't damage the device. What it does is it puts it in program mode, which means that it won't deliver a shock should that shock be needed. Most people who wear these, I have a friend of mine who has a pacemaker fitted, and she can't lean over a loudspeaker for a music system because that's enough of a magnetic field. And what happens is the device vibrates inside their chest. So most people who wear them or have them implanted understand that that's what happens and know to move away. There's some data here on the limits, but just be aware, it's a relatively easy calculation to make. How do we mitigate against high magnetic fields? Screen twin coil cables, twisted pair cables is a great way to reduce the magnetic field. The magnetic field itself, as I said, is not due to the battery pack, it's due to the current flowing in the wiring. Again, this means that your external wiring should be done with a correct cable. Don't just use any old scraps of cable you find around the workshop. An interesting one here is that in no circumstances should the high HV cable ever be coiled up. Cut cables to length and make them fit. If you coil cables up, because it's easier than putting a new connector on the end, you get twice the magnetic field per loop that you put in that cable. Our next hazard we talk about is arc flash. I believe the SAE gives some data on arc flash training and stuff on its website. This is what an arc flash looks like. We're looking here at only 45 volts and 5 amps. This is a typical spade connector. It's being pulled out by machines because it's pulled out at a controlled rate to maintain the arc. Initially, arcs are very hot, somewhere around 4 times the temperature of the sun. You don't really want to be over it when it happens. For those of you in the room, if you look at the screen, you can see on the spade connector there's a portion that used to be straight across the base of that tip. That metal has vaporized as part of that arc. I have done some teardowns and some failure analysis of some big gen sets where I've seen arc flashes on stators and rotors punched through a 1-inch thick steel casing. It's a real hazard. Some 2,000 people every year are damaged treated for severe arc injuries. The mechanism is you get a massive release of heat. That heat causes an expansion around the air surrounding the arc, which can create big enough blast pressure to create some 200 PS, 2,000 pounds per square feet, if you're close enough to it. A lot of the damage is not actually in burns, it's actually the impact damage. People have been knocked off the ladders and knocked off of their feet and helped something else. How do we mitigate against arc? Never ever remove a cable that is under load. Be careful when you are working inside the pack. We had a close call at one of our sites where we were disassembling a pack and somebody caused a short, drilling out a rivet. It only created a low energy flash, but if I would count our battery manufacturer plants as experienced in this. If we can make mistakes, so can you. The HVIL connectors are great. If you can get them and use them, my recommendation is that you do. It's another safety protection. Hazard number 5 is water ingress. What you're looking at here is a photograph of a Chevy Volt, which caught fire after a side impact crash test at NHTSA. It's fairly typical typical process that after a crash test, you take the initial measurements and photographs, and then you move the vehicle out to what we used to refer to at Myer as the graveyard, where it's then left for people to do further analysis should they want to. People went away at the end of the day, came back the following day to find that the graveyard had burnt to the ground. This, at the moment, for you, you need to think about rain and water ingress. If ever you move to liquid cool packs and you're using glycol, when it dries out is flammable. So if you get spills, that residue is flammable. So what was the failure mode here is that the water was inside the pack, or the coolant was inside the pack. That allowed electrolysis to occur due to the residual voltage inside the pack. It doesn't take a huge amount of flammability for oxygen or hydrogen to occur. And the best ideas came up that there was an influx of gas inside the pack, and there was enough heat generated as the cell started to fail to create an ignition source, and that's what started the fire and explosion. Different cell formats, the 18650 cell. This is a bit of background. We're now going to talk about how cells fail. The 18650 format, the pouch cell, and the prismatic cell, they all fundamentally work the same way. Do you buy in cells? You don't manufacture your own cells? Yeah, that's a good plan. Making cells is really hazardous. I'm glad we don't do that at Cummins at the moment. It should be noted that every one of these cell designs has an intended failure mode. When there gets an overpressure or something goes wrong with the cell. On the 18650, it's a number of vents around the anode. The pouch cells have a thin seam. It's a mylar pouch that's designed to burst as that pressure increases inside. And there is actually a vent on the prismatic cells. All cells, regardless of design, have an anode and a cathode, or numbers of anodes and cathodes joined together, along with a lithium ion salt inside. We talked about the Samsung failure. The Samsung failure was this separator, this insulator. It is porous, it is electrically insulated. This allows the ions to transfer to and from the cathode to the anode, depending on whether you're charging or discharging. I'm not going to go massively into cell chemistry because I'm not an expert on cell chemistry. I know enough to be dangerous. So what happens when a cell fails? What we're looking at now is we're looking at an overheating test. This is a standard URLL test. So European Council for Automotive Research, who dictate, I don't know, about six different tests. This cell is going to fail. You'll hear a clicking. That clicking is an ignition source designed to ignite any volatiles as they vent from the battery, so we don't get a build-up of gas. We just ignite it and let it burn off. You'll see even now there's wisps of smoke coming out. This is the volatiles. They initially ignite, and now the electrolyte is starting to boil off. The initial volatiles extinguish themselves. Everything looks good at the moment, other than a bit of smoking. But you can see the cell is still active. If you're still around when the cell does this, you need to restart. When cells fail, get out, get everybody else out, leave it to the professionals to deal with it. We talk about URLL ratings. URLL ratings you see from the tables have different hazard levels depending on how aggressive the cell fails. There's a number of tests from short circuit through to narrow penetration and thermal crushing rather. The test you just saw was a thermal stability, so that was heated to 130 degrees C while it was under load. That particular cell we looked at failed at a URLL level of 4. That's a typical automotive cell. Sorry, that was 6. Most automotive cells are tested and rated at a URLL level 4. This allows that 50% of the mass of the electrolyte will vent out, but there shouldn't be any flame, fire, rupture, or explosion. That one, interestingly, didn't count as an explosion because there was enough of the cell left to identify it as a cell. The SAE also has a standard for defining these hazards. One thing you should be aware of, it is illegal to transport cells unless you are trained and certified to transport cells. By transporting cells, I'm talking by sending by FedEx or some other shipping company. You're okay to carry them in your own vehicle. They are a Class 9 hazardous material, and your cell manufacturers and suppliers will have undergone these tests. And if you were putting your packs and modules into production and you produce more than 100 of them, you would be expected to do these tests. Typically, the cost of doing these tests for a pack or a module is around $25,000. Everything Cummins makes has to go through this test at least 3 times. So once at the module stage, and then once at the completed pack stage, as we transport modules and packs. The fines are fairly severe, and this is a worldwide standard, it's a UN standard. Don't be caught out. Looking further at cell venting, what you're looking at here, this is an overcharge test. It's a single pouch cell inside a barrel, which is inside a 20-foot ISO container, standard shipping container. So this is to give you an idea of how quickly the smoke can generate in a failure, and that there are early signs. This one's a slow starter. So if you push a cell far enough, it will fail. And it will vent. The venting is the first stage. The gases that you see in here are a mixture of carbon monoxide, carbon dioxide, and hydrogen fluoride. The carbon monoxide and the hydrogen fluoride are the 2 you want to worry about. One's a silent killer. The other one creates hydrofluoric acid inside your lungs and will burn you from the inside out. However, it takes, generally speaking, several minutes, even in a chamber this size, to reach the hazardous levels. As soon as you see a cell fail, smoke coming from a pack, get away from the pack. If you're in a building, evacuate the building. What can cause a cell to vent? Manufacturing defect causing an internal short circuit, like our friends at Samsung have issue with. Overcharging, so be careful whoever's designing your BMS. Cell over temperature due to overcurrent, again, that's down to the BMS. Failure of pack cooling systems, packs and vehicles being installed in a very hot location. Talking seriously hot here, like you need to reach 130 degrees centigrade before you get to that temperatures which they should fail at. Failures 2 and 3 and 4 should never lead to a hazard, as the battery pack should have its own redundant internal systems to detect them and shut the pack down. 1 and 5 can usually be detected by the pack, provided the pack is switched on at the time. But once it starts, there's not a lot the pack can do about this. So self-venting, what do? Have a procedure, understand the procedure, and follow the procedure, which basically should be get out, call the emergency services and tell them there are lithium-ion batteries involved. Fire is the next thing we talk about here. For automotive packs, you have to, in Europe, you have to undergo a fire test under ECE Reg 100. This involves placing the pack over a roaring flame for 130 seconds. Why 130 seconds is because 2 minutes is considered a standard egress time from a crashed or damaged vehicle. And the extra 10 seconds, I think, was because it was formed by a committee. This can be a side effect of cell venting, as we've talked about, but does need an ignition source to happen. It can be caused by internal arcing. And there may have been another cause. For you guys in Formula SAE, you're generally not going to get close enough to another damaged vehicle to be exposed to fire. But you can appreciate that when we talk about automotive packs, the risk of one of our vehicles being involved in a fire created by another vehicle is certainly a realistic one. And again, your gas release may include carbon monoxide and hydrogen fluoride. The pack is not intended to work after this test. It's just not expected to contribute to the fire. So this is an overcharge test again. This test takes 2 minutes to run. We run it in twice speed. The reason I run it in twice speed and show this video is that it gives you an idea again that there are early signs of failure. It's not a panic as soon as you see it. Act responsibly, get out, get your teammates out, get the rest of the building evacuated. Again, running, do something. So already there are signs that pack is failing. There's smoke coming from it. At this stage, if it was in one of my labs, I'd switch off the power supply and still evacuate the building. Once it gets much beyond this, I'm not going to worry about switching off the power supply. I'm about getting out. Putting out cell fires is not a job for you. It's a job for the professionals. Only use a fire extinguisher if it's to get yourself past whatever's on fire. By this stage, you certainly want to be on the way out of the building. Now you understand why I blew the door off that chamber at GM. Again, what do you do if you're involved in a fire? Stop using the pack and evacuate. But again, tell emergency responders that there are lithium-ion cells involved. It just means that they absolutely go into the building with breathing apparatus on. So let's look at how you can put the fire out when cells pack. This is a 18650 pack. Same chemistry as you're using here at Purdue. We'll use two heating blocks on the end of it to set fire to it. You can see as it ignites in the picture on the left. On the right, you can see the damage to that pack. That was when it was just left to burn out, and eventually the fire lost its energy and expired. You first thought it's an electrical fire. If I have to fight it, I have to move it. CO2 extinguisher is the ideal extinguisher to use. First thing to note here is you're generally not speaking of an electrical fire, you're talking about a chemical fire. So we put this in a fish tank, put it out with a CO2 extinguisher. CO2 extinguisher will knock the flames down. It will enable you to get past that pack to evacuate. But it will, generally speaking, reignite because you can't take enough heat out of the cells. And they just create their own oxygen and then they restart and reignite. Powder extinguishers do much the same. Again, I'll give you about a minute. Low expansion foam, this gives you an extra minute, partly down to the cooling effect because it's carried by water. But again, you can see you might as well have not bothered from protecting the pack because the damage isn't quite the same. The best way to put out a lithium-ion fire is using high-pressure water. And lots of water. We talk in terms of the combustion triangle, that to have a fire, you have to have heat, fuel, and oxygen. If you remove any one of those, the fire will extinguish. The only thing we can remove in a lithium-ion fire is heat. And the best way to do that is water and lots of it. The last one I talk about is weight. These are from the HSE, the Health and Safety Executive in the UK. OSHA's numbers are fairly similar, although obviously double that because they're in pounds. Any of you that have tried to lift lithium-ion cells, packs, and modules understand that they're heavy. Our current production pack, our big pack, weighs 550 kilos. So they are significant. And hazards are real. Just lift with the knees, don't bend over. Use supporting jacks when you're putting them inside the car. It's a silly injury to get at a racetrack. Final slide here is just a basic checklist. You know, understand and read the instructions supplied by the cell manufacturers. Write your own instructions for your packs and modules. Understand that you know where the fire extinguishers are, insulated hook, safety gauntlets are kept. And always try and have at least 2 suitably trained people working around. When a car is energized, make sure there's is somebody keeping an eye on everybody else's work. Well, Martha, that's all I've got. I'll wrap it up here. I don't know whether there's any questions that want to come to me after I shut down the WebEx, but thank you for giving us the opportunity to talk.
Well, I want to thank everyone for joining us for our first SAE CDS webinar powered by Cummins. And look for this one, follow Facebook, and you'll see the information.